Made in Chicago track. We have still two more presentations for you today. And continuing on from our talks from our friends at Lightbend, Dean Wampler would like to introduce how to use machine learning in streaming data pipelines. So,
thank you. All right, thanks for coming. Two requirements. One, do not throw bottles at me because I bruise easily. Two, if you want a beer at any time or nice coffee, feel free to order. Don't just wait for me to finish. Or you'll get really thirsty, I guess, if I'm following my own advice. Okay, so this is a talk about what it takes to use machine learning in fast data pipelines. So this is how to make money the easy way. The pictures, if you've never seen any of my talks, I just put pictures of my talks that I've taken. This is Yosemite. And there's other pictures from Oregon and Nevada. Oh, and if you want to get the slides, they're actually already at my vanity website, polyglotprogramming.com/talks. It's there. It's called an executive briefing, but I've toned down the executive stuff and amped up the developer stuff in this version. But the slides are pretty much the same. Okay. So this is kind of based a little bit on this generic book I wrote. This is one of those O'Reilly little reports. You've probably seen they're like 60 pages that talk about streaming architecture, so you can get a copy of this if you want. It's free. What I do at Lightbend is boss Boris around a lot, mostly. Somebody has to do it. Chicago police, they have requirements. Anyway, I developed lead a team that develops this sort of streaming part of our platform, which is, it's a bunch of microservice stuff. That's the thing in the middle at the top, and we're doing a lot more with Spark and TensorFlow and stuff, running on Kafka as a backplane, etc. So if you want to spend some money, I'd love to take it from you. I do take credit cards. And actually, recently, we're kind of excited about this. We released a component of that called pipelines. It's designed to make it easy to build streaming data pipelines with Akka streams or Spark streaming. And then when you deploy them, you get nice visualizations of what's going on. So anyway, that's all I'll have to say about marketing stuff. So what we'll discuss, again, this is started as an executive briefing, but I think for this crowd, I'll probably accelerate through the bit about why streaming, because you may already get it. Talk a little bit about the challenges of mixing data science and data engineering. Very briefly about how to get started with AI in your environment, and really briefly. Mostly talk about issues of actually serving models in production and what that means in a streaming context. Talk about some of the systems that you can use that are like all you can eat kind of packages that are nice. And then finish with a couple of pragmatic challenges you have to think about. Okay, so we're used to doing a lot of data analytics in batch, right? I mean, this is sort of the reason for Hadoop was just get as much crap as you can in HDFS and then run massive jobs over it to analyze it. But why are we trying to argue that streaming is so important now? A lot of it just comes down to timing. It's money. Like if in the energy industry, which obviously a wind farm is in that industry, you've got all kinds of need now to manage the grid because it's a lot more dynamic than it used to be. Because things like wind and solar they're quite variable. So managing the inventory is actually a real challenge, and how to store it too. But it's also an IoT problem. Each of these devices is spitting out telemetry. I remember a few years ago watching a video from Scotland of a turbine that was like burning out. It was on fire and it was still spinning away. So they like to know when that's going to happen ahead of time. So they like to monitor these things. A lot of the same problems apply in medical, whether you're trying to make sure you detect an arrhythmia immediately or offline, be able to provide access to someone's X-rays or something. In finance, it's everything from very high frequency trading down to maybe longer latency trading, but more intelligent algorithms. Because you can't. Well, we're hitting the limit of time of flight for the speed of light, right? So they can't get any faster. So now they're trying to get smarter, as the general rule, maybe with a little less speed. Telecom is an interesting one because it's everything from IoT to managing this network and people live doing sessions and calls. all the back office stuff. I did a project recently with a telecom where I helped them on this project, where they were like during major sporting events, they wanted to analyze all the activity on the network related to that event, and then like target ads to people, and even like target things like Twitter campaigns and stuff live based on what was going on at the sporting event. And of course, that doesn't work if you're not going to find out for an hour what people are actually tweeting about or whatever. And then, of course, we all know about mobile apps, how important that is. I found this state-of-the-art phone. Actually, this is one of the best phones ever made. This Nokia was indestructible. And it fit in the pocket really nicely. I mean, it's a little thicker than this guy, but yet it would still disappear in a pocket. Still kind of looked like you were happy to see people, maybe, but nevertheless. One of the important principles, though, like I said, time equals money. A more precise definition is that the value of information that you extract from data has a half-life. It just is less valuable over time, right? Like the telecom example, an hour from now, I don't care what people, well, maybe I still care, but I really wanted to know an hour ago what people were tweeting about, not now. Okay, so that's sort of the motivation. Hopefully that's not news to anybody here. Oh, and by the way, the other thing you can do, any questions? I mean, we're a small group, so any questions or whatever, just feel free to interrupt. So what about data science versus engineering? How many of you actually work in an organization where you have a non-trivial data science team and engineering? Probably almost all of us. If you don't today, you probably will before too long. But we have this sort of Mars versus Venus problem going on, where the data science folks, they have this love affair with this crazy language called Python. I don't think it's going to succeed, but it's only been around about 30 years. But anyway, almost all these tools are based on Python, and it's an obvious choice because it's a very simple language to learn, and these folks are not interested in learning languages; they're interested in analyzing data, of course. Whereas we developers, we're kind of used to working in stuff that's hard because we like suffering, I think, like JVM-based stuff and Go, because we love vintage 80s languages, cloud environments and so forth. And there's sort of this gap between the two, right? How do we bridge these two? I won't get into a lot of details about some of the interesting things that are going on to actually bridge them, to make it possible to run the stuff on the left on the infrastructure on the right. But we'll get into it a little bit as we go. Actually, one of the interesting things that's happening that isn't in the talk, and I'll just mention it while I think about it. Some of you may have heard there's this new VM from Oracle called Grail VM, G-R-A-A-L. And one of its nice features is it makes it much easier to host languages. People found ways to get like Ruby and Python running on the JVM, but it was always a bit of a force fit operation. Grail's a lot more flexible about this, as well as being generally more performant. So one possibility is that we'll just all be running Grail VMs and paying Oracle money for the enterprise version. And then all of this stuff will just run on top of the VMs. That's one possibility. Now and it actually also supports native codes, which is a requirement because most of these tools are using native libraries to get the performance, like to target GPUs and stuff. So that would have to work, or else it's a moot point. You can't just be interpreted Python. But if you think about this sort of the worldview of these two camps of people, there's some interesting things that kind of emerge. One is that data scientists are actually completely comfortable with uncertainty. They are used to statistics and probabilities, where you don't have an exact answer. You have, well, it's probably this with this amount of error bars or whatever. Whereas we engineers, even though we just like certainty when we can get it, even though we sort of are living in denial, because distributed systems are inherently unpredictable as well, within bounds. But anyway, so there's kind of a different way of thinking about the world. And I'll come back to how the implications of this as we go. Data scientists are less about these sort of CI/CD processes that we developers love, where there's this long chain of events that leads to deployment. They're more about iterative, experimental stuff, still working within the scientific method, hopefully, but much more about kind of the exploratory, sort of more informal process. Whereas, like I said, data engineers, the regular software people that do the plumbing, we're a little less comfortable with any sort of uncertainty that we like to squeeze it out of the system as much as we can. and we tend to be more process-oriented. Now, a friend of mine, Nathan, many of you may have heard, he speaks a lot at Strata conferences and so forth. He made the interesting observation recently, the Agile Manifesto does not mention data at all. If you know the Agile Manifesto, it has sort of general principles about software development, but it doesn't mention data. This is a link, I'll have it at the end too as well, to a talk that he did at Strata recently that I thought was very insightful. It was a talk about data governance, but he talked about issues like this, in particular, the kind of mental boundaries that we have to circumvent sometimes. Another thing that you realize if you start doing streaming is that it kind of imposes new requirements on your environment that maybe weren't there so much when you're doing batch analytics. And namely, it's the problem of, when I launch a batch job, maybe it has to run for a couple hours and then it's done. It might be this huge Spark job that's going to look at terabytes of data, but after a few hours, it's done. But if I start a streaming job to do those same analytics incrementally, that may have to run for weeks or months. It's going to see everything that could possibly happen if it runs long enough. Network partitions, hardware failures, spikes in traffic, like big game days and stuff. And so suddenly you have a lot more challenges to make these things reliable and to handle both faults as well as surprise. I use the word surprise here for the things that I didn't anticipate, like, oh my gosh, people actually do like to shop on my website, that sort of thing. Availability, typically these have to always be on because we're doing streaming because, again, time is money and we want to get answers faster. So if it's offline for an hour, that's typically really, really bad. Whereas if a batch job crashes at 2 a.m. and I can restart it at 7 a.m. and maybe that's not such a big deal, that sort of thing. And then for some definition of low latency. Now, a lot of people, unfortunately, get carried away with the idea of doing low latency computing when actually they only need the answers within an hour, or maybe tomorrow's good enough. So I do, even though we sell streaming tools, as I mentioned earlier, I do try to remind people that, if you can live with batch jobs, your life is going to be so much easier, so just do batch, for Christ's sake. But if you really do need streaming, because you really are doing high frequency trading or something crazy, then okay, fine. And then, of course, in order to handle these loads, we have to have some ability to scale up and down, ideally automatically, although that's kind of very hard to do in most of the systems that we work with even today. And I'll come back to this point in specific, but I'd like to be able to modify the behavior in some controlled way rather than have to restart things. And in particular, we'll see this will come up when we talk about model serving, where I'd like to be able to update the models as I retrain them without having to restart. And this is, in fact, what Boris was talking a lot about the last hour. Well, a lot of these properties are things that we've gotten used to actually working with in the microservice world. So in a lot of cases, if we just apply those principles, then we can meet these kind of new requirements even in the data space. So that's another area where there's kind of a merging happening between classic data science and even data engineering and microservice engineering, where they're kind of bridging the gap a little bit. Okay, so suppose you want to start deploying machine learning, where should you start first? Well, actually, the obvious answer is, and this is taken from a trend, actually a O'Reilly post about trends in AI adoption. And the obvious thing is, you have existing applications, you'd like to enhance their behavior with smarter analytics, so that's where you might use this stuff first. That can actually be a challenge if those existing systems are not very amenable to enhancement or incorporating new stuff. It could actually be harder than maybe a greenfield case. But usually, that's the logical place to do, is to try to make things better than you're already doing. And you've also got a baseline, right? So you can actually see if deploying a neural network is actually giving you better recommendations or actually worse recommendations, if you have a baseline of what you've used before. One of the things I'm kind of interested in, and I only explored this a little bit, is how can we integrate stuff that we've been doing for a long time, like expert systems, into these more modern approaches. I did a little prototype recently using rules, where we actually used it in a streaming pipeline. We didn't integrate it with machine learning in any way, but we did use rules of this really old system, actually. You're very object-oriented, kind of crude in a lot of ways by modern standards, but nevertheless, a great way to specify rules of behavior. There is some research work, and I need to find some links. I actually have a bunch of references at the end of this deck, and I need to add some to this, but there are people who are thinking about, can we make training faster and smarter of models if we actually embed domain knowledge ahead of time? Like sort of the classic way we train neural networks is we just kind of throw this thing at data, and it's completely stupid at the beginning. Like, all the weights in the model are completely random or whatever, and then it actually finds information on the fly. It's sort of almost miraculous, but it's also incredibly expensive to do it that way. So if I could pre-train the model, well, there's other ways to do this too, but if I can actually leverage what I know already and I can bootstrap my training, that would be better. Or at runtime, somehow combine the two. There are times, well, I mentioned this earlier, that a lot of these machine learning models are very probabilistic. If I already know that the tax law says that if you make over $20,000 a year, you have to send it all to the IRS or some rule like that, I can certainly hard code that rule. I don't need a neural net to figure that out for me. So there's a balance here. Okay, let's start peeling the onion a bit and talk about serving models in production. And I put a cloud here because this is where it gets a little ugly. So actually no, this is a survey from Kubeflow. If you don't know what Kubeflow is, I'll come back to it in a minute, but it's a project for a machine learning system on Kubernetes. But they did a survey recently of their users, and I know this is a bit small to read, but the number 3 item on their list was people had challenges taking models to production. And number 1 and 2 on the list were the sort of things we already all know about if we work in data at all, like how do I even get started with infrastructure, and how do I do like data cleaning and prep and all that kind of stuff. So a lot of stuff that was kind of typical, but this one's pretty interesting that popped up number 3 here. So Lightband, actually this is already published. In fact, we've done a survey recently. I need to update this with the link to it, but some of the areas where we found our customers were struggling with were things like, if I get this wrong, I'm going to miss business opportunities. I'm really worried that my data team will just, like their productivity will drag to a halt if they're wrestling with just mundane deployment problems or whatever. I don't want to get be flat-footed and miss market opportunities, and I really don't want my customers to be disappointed because I'm not giving them the best quality service. So these are not too surprising, but nevertheless kind of emphasize why people are really looking at machine learning as kind of their savior in some ways. Another problem is if I'm going to deploy stuff in production, there's a lot of control that really I need to really know what's going on, to know when things are going wrong, and to do things like auditing, which I'll come back to at the end. But hopefully my development team has already got this great process for continuous integration and delivery. So how do I integrate that with my model serving stuff? Like, should I be like doing version control of the models so I know exactly what's being deployed at every one time? Can I build automated testing and builds and so forth so that when someone does a PR to an integration branch, I automatically kick off the sequence of tests to make sure that the model meets some sort of quality metrics. And then how do I launch it? There's all kinds of stuff we're used to doing now, like dark launches, A/B testing, and so forth that we might want to be able to do here as well. It's absolutely critical, like it always is in production, to monitor what's going on. I don't want to deploy a model that suddenly takes twice as long to score records, because that probably impacts quality of service. Similarly, I'd like to know if it's actually better than the previous model that I deployed, and all that kind of stuff. So usually we have to figure out what kind of quality metrics can we assign. This can be really tough, like for recommendations. If I change how I recommend stuff to you to buy, well, maybe one metric would be how often do you actually click on that item, and even better, how often do you actually add a recommended item to your shopping cart or whatever. But other things where maybe it's not so obvious how to measure that it's actually better. Suppose that you're using models to score, like to approve loans for mortgages, let's say. And somebody, files a complaint with a regulatory agency that claims that you denied them a loan and they think that you were discriminated against them because you were in some minority group or something. So the first thing you're going to need to do is to go back and find out, which model, which version of the model actually was used to score that decision. What made it make the decision one way or the other? Maybe even I need to know who's accessed this model. Is it possibly somebody tampered with it? Maybe. I might even know how it was trained. If I'm really diving deep into why this model is behaving the way it is, I might need to know exactly what records were used to train the model. So this is a whole bunch of stuff that now I have to keep track of about my models. So effectively, models become data. They're not only data in the sense that this is one of the ways that they can be used in runtime. Forrest talked about this in the last hour, basically exchanging models as parameters and then updating things in memory and so forth. But they're actually data from the sense of governance as well. But there are some different things. This is kind of a laundry list of stuff that's a little different. So normally, an organization, a data science organization, is going to need ways to do reasonably accurate quality processes for searching for ideal models, like the structure of the model, like the neural network architecture, to do experiments on reasonably representative data while preserving data privacy concerns. This is kind of getting into the whole hyperparameter tuning thing. And while all this time we're also worried about not only protecting the private information when people are playing with it for these experimental purposes, but making sure that we get fair models, that they're not discriminatory, understanding the lineage of the model and the data that was used for tracking all that, all the usual stuff. And the rest of this is a bit of what we kind of hit on before. But then this other problem too, that if I'm the engineering side of the house and you're telling me that I can't give you exact, like you put in this record, I'm going to give you this same score every time, but it's actually a probabilistic thing. Now you've introduced a measure of uncertainty that I didn't have before, and so I need to somehow figure out, how do I know that this is actually working properly? How do I accept the fact that now you've added this extra level of indeterminacy to my system that I didn't have before? Okay, let's peel the onion just a little bit more and talk about two architectures that you can use to actually serve these in production. And again, this is in like a streaming context. And because this is a bit small for this in the back, what I'm going to do is zoom in a little bit with the mouse. But there's actually three things going on here. The first one is, let's see if I can do this. This will be a bit interesting. Let's do it this way. That worked. No, that didn't quite work. Anyway, what's going on is, imagine that I have IoT devices and I'm looking for anomalies to predict when things are about to fail. This is a really common use case. So I've got telemetry coming in from the field from all these devices automatically. I'm going to ingest it into a log-oriented system like Kafka to capture the data reliably, at scale, durably, all that stuff, and then serve downstream consumers. So as Boris mentioned earlier, Kafka is like my data backplane or my enterprise service bus. If you have gray hair and you lived that long ago, that's sort of the same thing. But anyway, I'm capturing my telemetry in Kafka, and then I'm going to send it over to my training regime, which is this blue circle. So this is where periodically I'm going to take whatever data I need, whether it's just the incremental stuff since the last training regime, or maybe it's everything because I'm going to retrain from scratch. And I'm going to do model training. And I'm just showing Spark here as one way I might do that model training because it's good at batch and mini batch. And then we'll see another example in a minute with TensorFlow. So whenever that happens, and this could be hourly, daily, weekly, whatever, then I'm going to send the updated model parameters back to a new Kafka topic. I may also write them to storage for the auditing things that I mentioned, and also to do startup quickly. I just load everything in memory. But for now, in my running system, I'm going to write those parameters back to a new Kafka topic so they're available for whoever's doing scoring. And I actually already hit the button, so the scoring is the green section of this architecture, where here I'm going to use microservices like Kafka streams or Akka streams because maybe I care about low latency. you don't care about low latency, you can use Spark, which is, maybe second latency realistically. Flink is pretty good at low latency too if you have really big scale. But if you like using microservices, you're already comfortable deploying those, and it's nice if you can have a library that can do this kind of data stuff for you that's inside your existing microservice architecture. So anyway, that system is going to be reading not only the raw data to do scoring, but whatever the latest models are that show up in Kafka, and it'll update its in-memory representation of those models, and then do scoring on the fly. And if it periodically sees what looks like an anomaly, based on what the model says, it will write a record to a new Kafka topic that's going to be where the anomalies get written to. And then the last bit is just the regular microservices that I've been writing that manage things like sessions with the devices, that handle like pushing down patches and updates, maybe enhanced services like map services or whatever. And they'll also be watching that topic for anomalies, and if they see that, oh, it looks like device 5 is having a hard drive problem and maybe might fail, it can trigger whatever corrective action is required. Hopefully before the user even notices that there's anything going weird, right? That's the whole goal of this. So there's, like 3 big areas of concern. There's model training. I'm showing it all in the same cluster, but that could have actually been done in another cluster, whatever. There's model serving that happens in some degree of low latency, whatever I need. And actually in the anomaly detection, it doesn't have to be milliseconds because you're hopefully predicting something that's going to be bad in a day or whatever, but nevertheless. And then the regular stuff that I have to do with microservices. So this was an example of embedded model serving where I actually have the models like somehow embedded in my microservices as a library. The other possibility is that I just use a service, like TensorFlow serving, where now I'm going to keep all of the stuff, all the intelligence about model training and serving in one place. And, it could be I have a different TensorFlow training in a different instance it's doing serving, but logically one place. I don't have to exchange models anymore in my system. I don't have to rehydrate models in my microservice. I'll just make your RESTful calls or whatever to TensorFlow serving whenever I need to do scoring. And that actually keeps these guys a little simpler than microservices, but at the penalty of more overhead for the REST call. I'll actually go through the pros and cons in just a minute. So I stole this picture from the TensorFlow documentation. You can't see the details in the back, but it's pretty much what you would expect. There's some opaque API, clients make calls. Behind the scenes, I manage all the models that have been given to me, like different versions of them, or like forests and models or whatever. And then you do the scoring as fast as I can as these requests come in. Okay, let's talk about the pros and cons of model serving as a service versus embedded model serving. Well, as a service is a really familiar pattern. All of us engineers have used services for a long time. We're used to this idea from microservices where we have like a REST API or maybe gRPC or something. And it does nicely separate concerns. So I have my brains in the data science organization to worry about all the this weird neural network stuff. I just have to know how to make a REST call and don't have to think about it. So that's nice. And that means they can not only have that expertise, but they can have different schedules for deploying new systems. Maybe they add another alternative to TensorFlow or whatever. The disadvantages are we are making a non-trivial amount of overhead calling into TensorFlow. It's probably on the order of milliseconds versus a function call that's on the order of microseconds. Although the time it takes to process the model could swamp out any of that overhead anyway, so it's not clear that this is actually bad. But, yeah, you could lose your network. So you would have to have logic in the microservice that can handle the case where it doesn't get an answer or nothing ever comes back. So it just recommends that you get the meal or whatever if you're in a restaurant. And this, if you're running entirely different systems for model training, like whatever TensorFlow does, and that's totally different than your toolkits for microservices, well, now you have to figure out how to manage these two different kinds of systems in production. That's what the second point's about. However, the advantages are, now we're on to the embedded model serving, where again, I have the model serving library embedded in my microservices. I get the lowest overhead. I still might have a lot of overhead processing the model, like a neural network would be expensive, but I don't have inter-process communication overhead and the reliability issue that Doris mentioned. And it gives me the ability to like tune everything in one place. So I'm actually thinking of proposing a talk for a conference basically about the revenge of monoliths. I'm kind of, I think we've kind of gone a little too far sometimes with microservices. There are times when it's actually not so bad to have a lot of stuff in one place. Yeah. So you heard it here first.
No, I've been saying this for 5 years now.
Yeah, but nobody listened to you, Boris. You should have figured that out by now. There are some big disadvantages. It's not rocket science, but it is somewhat complex to figure out the interchange format with like PMML or whatever. Make sure that both sides of both model training, model serving tools that might be entirely different support both kinds of models, support the interchange format. There is this coordination process. So it does actually raise the complexity a little bit if you embed model serving in your microservices. Like I say, it's not necessarily bad, but it's a downside. And actually, one of the real challenges is making sure that they are actually compatible. That if I do logistic regression, it usually works. If I do neural networks and TensorFlow and then like Big DL embedded in Spark, am I actually getting the same results from both of those systems? I have to make sure that actually works if I'm not using the same system on both ends. Okay, so the key thing about the last couple of slides is really, this is what you should do if you need to really take control of what's going on for whatever reason, either to optimize performance, cost maybe, as well as latency. And you don't want to just kind of like, adopt some all-you-can-eat kind of system and just kind of live with whatever its limitations are. You need to take control. This is a good way to do it with these kind of architectures. But I think you should think about some of these all-in-one systems and see if they're good enough for what you need. And in particular, there's 3 that I have listed here. I actually have more links at the end, but Kubeflow is the one I'll talk about in a minute for Kubernetes, just as a representative example. How many of you have actually used Kubeflow? Anybody? One person. What about SageMaker and AWS? Is anybody looking at that? Yeah. Okay. And MLflow is kind of a more not as broad a scope system, but really oriented, or comes out of the Spark community at least. This is what they all more or less try to do. Is if you think about a whole pipeline of stuff you have to do in a real world data science environment, everything from training to serving, it's all these things starting with data ingestion and cleansing. Hyperparameter tuning, including exploring the space of possible models. And so what Kubeflow and SageMaker and all these guys are trying to do is give you like one place to kind of do all of this in an integrated way. Most of them are bringing in a bunch of other open source components to do various pieces of this and try to make it a reasonably integrated experience so that you can just use this one big system and it'll cover most of your needs. So you can certainly do that. It came out of Google, although there's a lot of other companies working on this. This is a Kubernetes system, although it will work with OpenShift since OpenShift is based on Kubernetes. And if you're really interested in this, Boris has written a shit ton of blog posts, I can use that word, on OpenShift and Kubeflow on the Lightbend side. Hey, well, it's good. Okay, it's a metric shit ton of blog posts. Sorry,
You're at the pub.
Okay, we're nearly done. Just yeah. All right. There we go. Yeah, almost done. Just a few pragmatic 2 things that you have to think about. Lastly, I said earlier that I don't want to have to reboot my streaming system to update the models. Okay. And also, I need to audit. So let's talk just briefly about those and what we've done. Why do I have to do model updates? Because the world changes. They use this fancy word concept drift, where the models are no longer matching what's going on in the real world. In a sense, they have a half-life as well. So periodically, I need to retrain them, and eventually we'll get to the point where we just do continuous training, but that's a bit more of a research topic. But that can be expensive, so there's also this calculation you might go through. Do I really want to take the hit of running all these GPUs again? Or can I just live with a shitty model? There's a lot of bad words here, I apologize. Can I just use a bad model for a while longer? So you make that trade-off. And if you decide, and if and when you decide to retrain, then you can either do like just the usual batch jobs that we've done forever for model training, where you take some subset of your data, maybe not all of it because you've been running for years, but some subset and retrain from scratch. There are some recently mature methods of like training in mini batches, so you can start with an existing model and increment to improve it. That's really what you should do in this case. And then there's this researching kind of stuff to actually be able to do it continuously, per record as you go, which hopefully will be the way we do it in, say, a few years. Okay, so that was one topic. The other one being auditing. So I just made a list of some of the stuff you might want to remember, like what kind of model was it? Was it a neural network, CNN? Was it a, forest, whatever? What are the parameters and the hyperparameters of the model, of a particular model instance? When was it trained? What data was used to train it? When was it deployed, undeployed, redeployed, whatever? We really do need quality metrics. We don't often think about this. Sometimes we do, but I need to know if it's working in some way. And I also need to keep track of how it's doing, like how many records has it scored, what was like the statistics of scoring. We can't assume it's Gaussian because it might be long tail, but what was like the average? Again, it's a bad number if it's not symmetric statistics, but I need to know that kind of stuff. And then the kind of details that I might be watching to decide when I have to retrain, like quality metrics declining or something. People just stop shopping. All right, I put a bunch of links at the end. I had to show this picture. I took this in Nevada, in a national park. There is actually a national park in Nevada called Great Basin that nobody knows about. This is obviously the Milky Way. How many of you saw Mars last summer? It was like really bright in Chicago. You could actually see it in Chicago easily. It was the closest approach in like 17 years, so it was really, really bright. So that's Mars. I mentioned this blog post from O'Reilly, 9 AI Trends. It's good. And then I mentioned Dr. Nathan's talk. I mean, these are all clickable links. I'll show you where to get the deck in a minute. I actually really like their weekly blog, or it's really like an email newsletter, their radar for data. There's another one for AI, and then they have some others for like systems and programming and stuff. Distill.pub is an amazing resource for very graphical, detailed explanations of neural network concepts, like training and hyperparameter tuning. So that's for the techies. If you're less technical, the algorithm and the gradient are really good. More general audience kind of resources for explaining a lot of the concepts. The algorithm is done by MIT Review, for example. A few links about research on like improving the ability to train on the fly. Links to these all-you-can-eat kind of systems like Kubeflow. Fiddler is a startup that's focused on the problem of how do I explain what the model's actually doing, which is another problem when you get into issues of like fairness and so forth. How do I know why it's doing what it's doing? A few more, actually the first link is that report I mentioned that I wrote, and then a couple of really good books on stream processing in general from O'Reilly. Some other talks I've done on streaming. And then, did you mention this tutorial? So Boris mostly, and I helped him write 2 tutorials on model serving and streams. Actually, some of the code he was showing came from the first one. And then general stream processing with Kafka and microservices. These are on GitHub. We've done them at conferences, but they're free to use. So if you want to play with the code. Yeah, and try your own production. Make sure you buy my stuff. And that's it. So thanks a lot. A minute or two for questions? Yeah.
I'm just kind of curious about your suggestions on how to store the models and also version.
Yeah. So for the video, how do I ideas for versioning and storing the models? It really depends a lot. Most of the time, this is text, like especially, so one way you can do it is actually take the PMML that you're outputting and just write that into a Git repo. So, you can even tag it right away if you wanted. Or you can take those parameters and write them into a database. A challenge would be if you like vary the hyperparameters, so the records are actually changing, like the number of parameters is changing each time, or the structure. I think it's probably less important. So here's the thing: these are not high volume kind of output, because again, you're not training very often. So probably anything you choose, as long as you can capture the data, it's good enough. You know, whether you're writing to Parquet files or CSV files, and then using Spark to query them, that's probably plenty good, as long as it's to a reliable file system. But you could, especially if you already have a system for data governance in your organization, then it would make more sense to maybe be writing to whatever databases you're already using as part of the data governance environment. But yeah, I might as well version every single one with some really good timestamp. One thing I did mention, and Boris probably has more comments on this, is like when you actually score a record, you should probably not only add the score to the output record, but also an identifier for that model version, so you know which one was used when you're debugging later on. Did you have more?
Yeah, if you look at Kubeflow, they've just started the new initiative that they are actually trying to take of the Kubeflow and make it more generic, which is model metadata, and they have multiple tracks starting from how do you capture the data that is used for the model creation, how do you capture the assumption up to the point, how do you capture the model usage. So this is work in progress, come back in about a year. That might be something that you can use.
Yeah, good point. Yeah.
The other question I had was that, what's your opinion of stability of AI system production? Are most of their approaches fairly stable, or are there issues with reliability or consistency?
Yes, the question was, what about how stable are these AI systems in production and reliable and so forth? You know, to be quite honest, I don't have a lot of direct experience there to really say. I mean, maybe Joe's kind of raised his hand. Have you seen them? Okay.
What you put in?
Yeah.
Where Bob so have asked answer. The systems are amazingly stable. The model can suck. That's the basic answer. But the system itself works fine. It doesn't care. It's the model, and you have to make sure if you've used supervised learning, the model is only as good as the data that you've used to train the model. So if you are trying to do machine learning on one set of data and try to put it in production on completely different data set, yeah, it's a crapshoot. It's a technical term.
Yeah, actually, a pet peeve of mine, you'll see a lot of like popular press talking about biased algorithms, and it's not the algorithms, it's the data that train them this bias. So anyway, okay, thanks a lot. Make sure you buy beer and coffee.
Yeah, for anybody who's joined us recently, you're welcome to come on up. He's happy to serve you a free iced coffee, if that's what